Um, Now, the first observation you should make when you when you have this picture in mind is, I have my convex domain and now I'm trying to minimize a linear function. So when like at the optimum, it will always be at the boundary of my convex domain, right? Because otherwise I could sort of move further in that direction and then I would, escape my domain. But the issue is that sort of like searching over the boundary of this domain isn't any easier than searching over P. Right? There's no reason that this should sort of be easier. And now the idea of like a specific class of interior point methods, like these path-following interior point methods, is what if we just don't try to search over the domain, but we sort of start inside the domain and we slowly try to move towards the boundary in a way such that the boundary points we go to is actually the optimum. And now, like one of the key ingredients is like you have to write down like a sort of barrier function, which explodes on the boundary of your domain. So it goes up to infinity. And then what you do is instead of trying to minimize like the function or like this linear function directly, what you do is you try to follow something called the central path. So what I do is I'm looking at this like function, right? My original objective plus this barrier, and my original objective I weigh by some number t. And now what I'm going to do is I'm going to sort of increase t in every iteration, and then move closer to the minimizer of this function ft. And now the idea is that when t becomes very large, the minimizer of this will be close to the minimizer of my original objective. Because as t becomes large, the relative influence of this capital F function, it decreases. So you can sort of reasonably expect this function to go, like this path to go to this minimizer. And now what you try to follow the central path, what you have to do is you increase like t slightly in every step, and then you want to move closer to it again. Right? And you have to do that somehow, and like the method of choice is to use Newton's method. So like you solve some quadratic equation. Now there will be a more technical assumption of this function f that will be a self-concordant barrier. These words are important, but they're not important for the next few slides. And now here's a picture of what I just said. Right, so there's the central path of these minimizers of these like t times my objective plus this capital F. And suppose I start close to it, like at some point p0, I start close to some z of eta 0. And now what I'm going to do in every iteration is I'm going to sort of increase my time parameter to eta 1. I take a Newton step and I end up at this p1, which you can see is closer again to the central path, right? And you just iterate this. And like the whole claim of interior point methods is this will converge to the minimizer. All right. So in the title, I suggested that we will do this on manifolds. Right, and it's maybe you're not familiar with manifolds, so I should tell you a little bit about what is a manifold and how could you hope to do it in that setting. Right, so for this talk, the definition of a manifold will be very simple. It's a space that looks locally like Euclidean space. So for instance, I can look at a sphere, right? And if I'm standing at a point on a sphere, then locally, sort of the surface around me just looks like a flat plane, if you don't stare too hard. Similarly, you can look at something like a hyperboloid, right? So this is also like some nice surface in our free. And you can also see here that locally it looks like a plane. So these are like the types of manifolds we care about. And now the important thing for us for this talk is that whenever I'm standing at a point, I can sort of, I have like a vector space, which is called the tangent space, which parameterizes the directions I can move in my space. So it's like sort of infinitesimally, this is like the directions I could take. And it's sort of, the elements of this thing are a little bit hard to define. Like it's not easy to get like a sort of canonical construction of this thing. But the upshot is that whenever I have a smooth curve, passing through my point, then the derivative at time 0 should exactly be an element of this tangent space. So it really is like directions I can move. So for instance, how do you get like a good description of these tangent space? If you look at, for instance, the sphere, then you can tell that like I'm standing at a point on the sphere. And then sort of the directions I can move in that sort of stay within the sphere are exactly the directions that are orthogonal to the point where I'm standing at. Right? This is like sort of a geometric description of what this tangent space should be. And if you know what tangent vectors are, then you can also define just derivatives of a function on your manifold. So what you do is, right, suppose I want to compute like the derivative of my function f in a direction u, right, in a tangent direction. Then what I do is I pick a curve that passes through my point, whose velocity at this point is exactly u. And then I just look at the first derivative of my function f along this curve. Right, so this is just basic differentiation of functions on manifolds. Okay, and you have to check, of course, that this doesn't depend on whichever curve you picked. But you know, it turns out that this is fine. All right. Now, manifolds by themselves are not good enough to do sort of interior point manifold. You need a little bit of extra structure. Right, so it turns out that sort of it's very convenient to have like a notion of distance. So what you can do is whenever you have a like this tangent space, what you can do is you can put an inner product of this. Right, so just like Euclidean space, there we have an inner product. Here, what I want to be able to do is I want to like measure angles between like angles and lengths of tangent vectors. And a Riemannian metric is exactly like a choice of such thing for every tangent space. Now, if you have this, you can also measure the length of curves. So if you have a curve that's parameterized in the unit interval, what you can do is you can just define its length as the integral of the length of the velocity vector at every point. All right, so this gives you a notion of length. And whenever you know how to measure the length of a single curve, you can also define a notion of distance between 2 points. So what you would do for the distance between 2 points is you just take the smallest length of any smooth curve between these 2 points. Right, so this just generalizes the usual Euclidean notion of distance. Now, what this metric buys you is it's not just a sense of distance, but it actually buys you something more. So it turns out that you can define some funny object, which is called the Levi-Civita connections. And what this basically allows you to do is, rather than just taking like first order derivatives of functions, as I was able to define on the previous slide, you can now also define higher order derivatives of functions. So the first order derivative is like, it just coincides with what you would expect from the previous slide, essentially by definition. But now I can also like make sense of something like a Hessian, right? So at every point, this needs to be a bilinear form on the tangent space. And more generally, like you can take the k derivative of a function, and this would be like a k multilinear map, so like a k tensor. Right, so I have some notion of higher order derivatives. And it's good to know that this Levi-Civita connection is uniquely determined by this Riemannian metric. So it's like, I call it extra structure, but it's not really extra structure. It's like God-given object. All right. Now, if you have a notion of distance, length of curves, you can also define what are like the analog of straight lines in Euclidean space. And like sort of straight lines in Euclidean space, what they are is between any 2 points, or at least sort of locally, I know that a straight line is sort of the minimum length path between the 2 points. Right, and you can take this as a definition also on Riemannian manifolds. So I drew some pictures of what they look like. So for instance, on a sphere, like a great arc like this, it's sort of locally, it's the minimum length path between any 2 points on this curve. So this is a geodesic. And similarly on the hyperboloid, you can look at this particular curve, and this turns out to be a geodesic. So I'm lying a little bit here because I haven't told you what the metric on this hyperboloid should be. It should really be like the sort of the restriction of the Lorentzian metric. So not just Euclidean distant measure, but you know. So the point is this generalizes straight lines beyond Euclidean space. And when we know what straight lines are, we can define convexity. Now it's convenient to also know that geodesics are, like whenever I'm standing at a point and I want to move in a particular direction, there's always a unique geodesic that passes, like that has this like sort of these initial conditions. And if you follow this geodesic for time 1, you get something called the exponential map. Right. So with that in hand, we can define convexity. So when do I call a function convex? Well, what I want is I take my function, and whenever I restrict it to some geodesic, right, I get like a curve, like I get a function from R to R essentially. And then I would just want this function to be convex. So you can write it as this estimate. So like f at gamma of some convex combination of times is at most like t times f of gamma at one endpoint plus 1 minus t times f of gamma at the other endpoint. And similarly, you can define convexity of some domain in your manifold. And here I take it to mean that for any 2 points in my domain, every geodesic that passes through these 2 points is also completely contained in the domain. Now you can complain about this. In fact, you should complain about this. For instance, it means that sort of the sphere has no like strict convex subsets. And you can, like, the reason this is true is because these great arcs are exactly the geodesics. But now if I take 2 points like then any great arc that sort of passes through these 2 points must be completely contained in the domain. But you can actually cover the entire space using great arcs that pass through 2 points. So there are no like sort of interesting convex domains. And in fact, like the same argument you can use to show that there are no non-constant convex functions in the sphere. So the sphere is like a sort of bad thing, but this hyperboloid, it turns out to be a good thing for us. All right, so I want to say a little bit about convex optimization techniques on manifolds. And the way I do this is by, like, I just take something Euclidean and I tell you, is there a Riemannian version of this? So, of course, there are like simple methods, like gradient descent. And gradient descent is easy to generalize to the Riemannian setting. What you do is, like, I compute my derivative and I follow the geodesic in a particular direction with the step sizes, you know, whatever you would expect from the Euclidean setting. And it turns out you could just analyze this in exactly the same way. Like for smooth functions, strongly convex functions, etc., etc. You can also do like sort of constrained convex optimization using like sort of projection methods like Frank Wolf. And, so this is like a slightly more advanced first order method. You can ask, is there an analog of like something advanced like Nesterov acceleration? Which is very nice in Euclidean setting because it reduces the time complexity you need to find minimizers. And it turns out that in the Riemannian setting, life is a little bit more difficult. There are some sort of geometric obstructions to getting like global acceleration. But local acceleration, sort of when you're close enough to the minimizer, is actually still a thing. All right, the next is Newton's method. And this is like also like a classical thing. People know just like how to analyze this. So this like these methods are all like reasonably good. Now, there are some more advanced methods in the Euclidean setting. For instance, cutting plane methods are amazing. We know you can use them to find like high quality solutions to convex optimization problems, but it's really not clear how to generalize this to the Riemannian setting. because it's not clear what planes should be. Right, this is like a little bit trickier, and we don't know any constructive method of like finding good cutting planes, and like the whole situation here for these methods becomes a mess. Also, the ellipsoid method, we have no analog of ellipsoids that we know sort of works. So we have nothing like the ellipsoid method. So like using any of these, it's not clear how to get like sort of good algorithms for high precision convex optimization. And in a way, for some functions, our work resolves this by also allowing you to use interior point methods, which are also good at finding high approximation solutions.
And a very quick question. For cutting plane methods, when you say there's this non-constructive, can you say roughly how it goes? Is it still pointing center of gravity now for a manifold and cut through it, or?
Yeah, so you need to restrict the manifolds you're looking at. We do know that there is like for non-positive curvature, we know that sort of good cutting planes exist, but we have no way of finding them.
And do they still go through some notion of a center, or this is like an entirely different way of?
Yeah, so they do still go through some notion of a center. But like there are more reasons why cutting plane methods are bad in this setting. And somehow, I'll get to that on the next slide actually. So the reason that these cutting plane methods are sort of, even if you could make them constructive, they would still be bad, is because like the geometry of the space can cause things like, can make your life just harder. So to find good optimization methods, you need to exploit more structure of the problem you're interested in. Right? These cutting plane methods and ellipsoid method, they're sort of generic. They apply in many situations. But IPMs require more structure. And now the reason that okay, in non-positive curvature, there's like this notion, or like in manifolds, there's like this notion of curvature. So there's some definition, you can write it down. And basically non-positive curvature means that whenever I stand at a point and I look at two orthonormal unit vectors, and I look at the geodesics that like emanate in these directions, then you can look at the distance between these two geodesics over time. And now non-positive curvature means these geodesics, they diverge faster from each other than I would expect from Euclidean space. This is like a sort of nice geometric definition. And now this is like there is some nice examples of these spaces, like Euclidean space. This has just zero curvature, right? Because I compare to Euclidean, like how the situation would look in Euclidean space. So in Euclidean space, the number should be zero. There's also like the canonical example, which is hyperbolic space. This is constant curvature -1. Important for us are the positive definite matrices with some funny metric. And now it doesn't matter so much what the metric is. The important thing is that the geodesics are not like, I take my matrix and I add t times Hermitian matrix. Instead, the geodesics are like, I take the sort of the exponential through my sort of essentially through the identity, and then I sort of move it to somewhere else. So this is like sort of an exponential version rather than addition. And there's a nice complex subset of this that we care about. Notably, this does not include the end sphere or something like an embedded torus. So the end sphere has constant positive curvature, which you can find out by an explicit calculation. Now, what are these obstructions that I was alluding to? So the reason cutting plane methods, for instance, are generally not satisfactory, even if you could make them constructive, is because the volume of a ball of radius r in a hyperbolic space, this grows exponentially with the radius. Right? In Euclidean space, you know that the volume of a ball of radius r is like something like r to the n up to some constants. But in even two-dimensional hyperbolic space, it scales like e to the r. Maybe I messed with the exponent, but so this means that if you had good cutting plane methods where you could decrease the volume of your domain in every iteration by a constant factor, if the only thing you knew was like that your optimizer was in some large ball at the start, some large radius r, then you would still need like order r iterations to get to something of constant volume. Right, because I can only decrease by a constant factor in every iteration, and my starting volume is exponential in r, so I need like r iterations. Right, so this is really bad for cutting plane methods. And now it turns out you can use this volume growth even to prove like black box lower bounds for convex optimization. As in, I can give you sort of like function and gradient axes, and then you can show that like the number of queries you need to make to this gradient oracle, it's at least linear in the distance to an approximate minimizer, even if you only care about sort of a very weak notion of the precision. This is relatively recent, and it's kind of annoying that this is true, but you know, it's the way things are. And now for the problems that we care about, where we means at least me and Rafael, we know that the solutions that we're interested in can be exponentially far away. So something like cutting plane methods or like first order methods, we know it will never give us efficient time, like polynomial time algorithms, because we can only like take sort of short steps. So we really need to use more structure to get efficient solutions to these problems. All right. Now let's get back to interior point methods. Right, so I mentioned on the first slide that there is, right, you need like some technical notion to make sure that you can take like these Newton steps and then increase this time parameter, right, for this path following method. And what you do in the Euclidean case is you assume some really funny looking estimate. So a convex function f I call self-concordant if the third derivative in any particular direction is at most 2 times the second derivative to the power of 3/2. Right, and you know, this is funny for many reasons, but it's also good because like this power of 3/2, it's a little bit annoying, but it's also good because if I now rescale this u by a constant factor, right, by some parameter lambda, then the left scales like lambda to the 3, and now the right also scales like lambda to the 3, precisely because I added this power 3/2. Right? It's sort of invariant under rescaling whatever I plug in. And you can think of this as sort of like it's a Lipschitz continuity of the Hessian, but measured in a sort of funny way. And the reason I say this is because for standard analyses of the Newton method, they assume like a Lipschitz property on the Hessian. But these assumptions are not invariant under rescaling your domain. Whereas I just tried to convince you that this is actually the case for this particular assumption. Now, of course, the definition is nothing without examples. So there are some silly examples like linear functions. They are self-concordant, right? Because the second and the third derivatives are 0. So I'm estimating 0 is less than 0. But also convex quadratic functions are self-concordant because the third derivative is 0. Right, so these are 2 easy ones. Now sort of the first interesting example, which is already hugely important, is minus the logarithm, defined on the positive numbers. So how do you verify the estimate there? Well, you compute the third derivative of this function, and you think, like if you think for a bit, you realize that it's 2 over x cubed. Yeah, right, the third derivative of minus the logarithm is 2 over x cubed. And the second derivative is 1 over x squared. If I raise 1 over x squared to the power of 3/2, what I get is 1 over x cubed. So for minus log, the left-hand side is 2 over x cubed, and the right-hand side is also 2 over x cubed. Okay, this is not a coincidence. In fact, I think it's the reason why people include a factor 2 here. I mean, it makes some other things nice as well. This is like sort of the canonical example. And what this, like the self-concordance of this thing, of this minus log allows you to do, is it allows you to give efficient algorithms for linear programming. If you use some sort of theory or algorithms. Now you can do something similar for minus the log determinant of a positive definite matrix. The computation here gets a little bit more hairy because, you know, matrices, but I can tell you that the estimate works out. And then there's like an even more painful example where I look at the set of like the sort of the epigraph of the exponential function. And then it turns out that this monstrous looking thing is also self-concordant. And this allows you to do, for instance, geometric programming, which is like another optimization paradigm that generalizes linear programming. All right. Now, what's good about self-concordance is that sums of self-concordant functions are self-concordant. And it's, as I said, it's preserved on the rescaling and like translation of the domain.
Can I ask you a quick question?
Yeah.
For some reason, I thought this 2 was actually like a lot more than it seems. Like this 2 is like it really needed to be 2 for some reason. Is that do I have the wrong impression?
I mean, you can pick another constant there, but then whichever constant you do pick, like it just appears in the later estimates.
Okay, that's it.
That's it. It's just people like to do this because it simplifies, like it makes some expressions look nicer. And it's also exactly tied for minus log, which is like the example. I mean, you can tell here that like this is minus log, this is minus log. There's like minus logs everywhere here. So, you know, there's a good reason for this too. Okay. So what you have when you have the self-concordance, you can do something with it. And I told you that you can analyze Newton's map with it. So let's see how that works. So what I do in a Newton step is, you know, I look at my function, I take its quadratic approximation, and then instead of just trying to minimize my function, I minimize this quadratic approximation instead. Right, and like the step I take in this iteration is called the Newton step, which I denote by NFP. And then I want to define this funny looking quantity, which is sort of like it's called the Newton decrement. It's basically the amount of progress you make in this quadratic approximation. But you can also recast it as like some funny norm of this Newton step, where the norm is sort of given by the Hessian of, or like the local inner product is given by the Hessian of this function f that you start with. And then it turns out that you can prove the following estimate. If I start with a self-concordant function, and sort of its domain is like sort of what it should be, which is like the definition of the strongly self-concordant. And my Newton decrement is at most 1, then you can guarantee that sort of the next point, like my point after taking this Newton step, it's still in my domain. And you have the estimate, like you have an estimate on what the Newton decrement will be after taking the Newton step. It's at most the previous Newton decrement squared, divided by something that's not too big. If you assume that this is like at most 1/2 or something, then you can think of this as like 4 lambda squared. Did I get 4 right? I think I got 4 right. Yeah. Okay, so this gives you like a quadratic convergence results because what you can see now is that if you start iterating the Newton method, where like your starting lambda is small enough, say something like 1/4 or 1/3 or whatever, then in every iteration you get like the square of the previous thing, so you get like sort of the quadratic convergence thing for the Newton decrement. And you can actually relate this Newton decrement also to like the gap in function, like the gap in the function value to its minimum. So this really tells you Newton's method converges quickly for self-concordant functions. That's the takeaway from this slide. Okay, so let's see how to do this on manifolds. And now here's scary looking definition. So I want to call a function like a convex function on a manifold. I want to call it self-concordant if, again, there's like my third derivative, but now using this Levi-Civita connection that I get from my metric. I want to bound its absolute value by 2 times like the Hessian evaluated on each of the vectors that I plug in. Okay. So this looks a little bit scarier than the definition that we had in the Euclidean case, right? Because now there are like 3 vectors appearing rather than just 1. Okay, and this is actually with good reason. It's because we know that this estimate, you need it to prove like the quadratic convergence result on the previous slide. And we know that this estimate is also stronger than just requiring it along like every geodesic. So that's like sort of the case where u, v, and w are all the same vector. Like we know examples of functions which are like for which the sort of the constant on the right hand side is different from depending on whether you use this u, v, w, like all equal or not. And there's a good reason for this. The reason is that the non-zero curvature of the space you're looking at, it implies that this first derivative is an asymmetric free tensor. And now, why is this relevant? It's because in the Euclidean case, the third derivative, if you look at it as a free trilinear form, this is symmetric in the arguments. So you can use a polarization style argument to say that sort of the symmetric norm with respect to this Hessian is the same as the norm over all inputs u, v, and w. And unfortunately, this just breaks it down in the Riemannian setting. Right, so you really need this is really a stronger estimate. Okay, and I have to say here there were some previous attempts at defining a good notional self-concordance on manifolds, but they somehow either they missed this or they just assumed this u thing, and then you can only prove some weaker results. For instance, this quadratic convergence result, you cannot prove it with just the weaker estimate. Right, it's just not true as stated. You can also prove other familiar results, and sometimes you do really only need this UUU version of the self-concordance, like the self-concordance from geodesics. For instance, you can show that ellipsoids of radius 1 are contained in your domain. You can show that that minimizers exist. You can do some damp Newton method thing, etc. Right, so in essence, of this part of the paper, I would say our main contribution is writing down the right definition. Right. Okay, so now let's see how to do this path following method. Right, and I said something now, not just self-concordance. I mentioned the word barrier, so I should define what a barrier is. And a theta self-concordant barrier is nothing more than a self-concordant function whose Newton decrement squared is always bounded by theta. So it's some type of Lipschitzness, uniformity, whatever estimate. And if you have an estimate like this, you can prove the following result. Right, what we were doing is we were looking at t times my objective function plus my self-concordant barrier. Now you can show that if this ft is still self-concordant, which is for instance the case if this f is a linear or quadratic thing, and the Newton decrement is at most 1/3, right? Then the gap in function value, right, for the objective that I'm interested in, this scales the parameter of this barrier divided by t. Okay, there's some extra term here which you can basically think of as 1, especially because it's not plus 1. So if you want to get an epsilon approximate minimizer of the objective over your domain, what you need to do is you need to just be able to follow the central path to time roughly theta over epsilon. Right, because then this upper bound just becomes epsilon. Right, so this gives us some grip on how long we need to do this interior point method. Now, of course, we have to follow this. In this path following method, I said increase the time slightly. Right, but that's a vague statement, so I should also give a bound on how quickly you can increase this time. And it turns out that okay, there's some funny looking statement that we call it, like, you can call it a time switching lemma. But basically what this means is that in every iteration you can increase the time t by a factor roughly 1 + 1 over square root of theta. So this means that if I would start at time 1 and I want to get the time theta over epsilon, then I need to take like square root theta log theta over epsilon iterations. All right, and you can write that down. Of course, you need a starting time, which is where some funny quantity here appears, but it's not so important. So what this result says is, I give you a good starting point, which is like close to the central path at time 0. Then you can optimize a compatible objective within a certain number of Newton steps, which scales like square root of theta log 1 over epsilon. And this quantity you need to bound for your specific application, but it's usually not so big. All right, so this shows interior point methods, also manifolds, are capable of giving like high precision solutions pretty quick. Right. Now I said here the word compatible. Now this captures, right, you can ask what type of objectives can I directly optimize by following this path. And basically, the thing you need to assume about your objective is that it's good enough to get some estimate on your objective such that this function is still self-concordant for all times. Now, this is automatically true for linear and convex functions, like convex quadratic functions, because their first derivatives are 0, so like proving self-concordance doesn't get any harder. But you can do like something slightly more general, which is also useful for applications. And this compatibility notion is also useful for constructing barrier functions. Right. So we have a bunch of theory, and theory is great, but what is theory without examples? Right. So for our scaling applications that we're interested in, the domain of optimization, it looks something like these positive definite matrices with this affine invariant metric. Right. So in particular, this had like this non-positive curvature property that I told you about, and the geodesics of like this exponential form rather than this like linear form. And you can show on this space the following result. You can show that the squared distance to a fixed point is a self-concordant function. Right. Now you may wonder, why is this statement non-trivial? Right, it's a quadratic function. Right, it generalizes quadratics from the Euclidean setting. So surely it should be self-concordant. Right, it's like the first place to look. But the third derivative of this function is non-zero. Even though it's like a quadratic function in the most natural sense of the word quadratic, it has non-zero third derivative. Right, because a general quadratic you can write as like the distance squared to a point of this one, basically. And some linear term, but who cares about linear terms? Right. And you can show it also that because we can prove this result of PDN, you can also show that on arbitrary symmetric spaces of non-positive curvature, the square distance is also self-concordant, but not so interesting for this crowd, maybe.
If I look on, but is this an example that if I look at like along every geodesic, you're gonna get 0 for the third derivative, right? If
No.
you look at even along geodesics, it's not gonna.
So it's only 0 along geodesics, which sort of points, like which pass through P0.
Okay, yeah.
But in any other direction, it could be non-zero.
Correct, because that's where the symmetry, right? It comes from, in those guys, then you have a truly quadratic function, and then. But any other geodesic from P to Q that doesn't pass by P0, then this function will not be. That's where, is that where the non-symmetry, like?
No, I mean, like
comes?
like the fact that these spaces are symmetric spaces is really just useful for being able to compute anything.
No, I'm saying, is there where the asymmetry of the third order tensor comes to play?
I mean, it's definitely where it comes in. It's pretty, like, but the first derivative should be non-zero in any space where you have like non-zero curvature.
Non-zero, right.
All right. So I just said that like this symmetric space thing, or like this PDN, it's very nice. And it's nice because here you can compute things, right? We have explicit expressions for geodesics. And evaluating the Hessian is very easy. You just look at your function and you like look at the geodesic in the direction you're interested in, and then you take the second derivative. So, you know, Hessians are easy. Third derivatives get a little bit more messy. So what you need to do to compute a third derivative, like explicitly, is sort of you look in the first direction that you want to go in, and then sort of the second direction you have to transport along this geodesic through the first direction. And then at this new point, you have to evaluate the Hessian in that thing. Right, so this transporting thing, it's parallel transport. And specifically for PDN, it's easy to write down like a matrix expression for this thing, which involves matrix exponentials. This is maybe all I'll say about computing these derivatives. Right. And if you have this like this self-concordance of this distance squared, we can also use it to construct barriers for specific domains. For instance, if you look at the set of points whose distance squared is at most s to some specific point, then you can write down some function that looks like this. Right, so there's like a minus log of s minus this distance squared plus some multiple of the distance squared. And you can show that this thing is self-concordant, and its Newton decrement at a specific point is bounded by something that scales with the distance squared to this point. Maybe I'm off by a square. So what you can, like, what this statement tells you essentially is that a ball of radius r admits a self-concordant barrier whose barrier parameter is like order r squared. Now this is much worse than the Euclidean situation. In the Euclidean situation, you can write down a barrier whose barrier parameter is just 2 for any, like a ball of any radius. So in this PDN case, you know, it seems that optimization via zero point methods, at least when it's over balls, is still pretty hard. Like I said, is the case for these cut and big ones. And on hyperbolic space, you can get like a refinement of this statement, but it's not so interesting. All right. So I want to talk very briefly about these scaling problems that I said are applications. And you may have heard of the matrix scaling problem before. But if you haven't, then the statement is simple enough that I can present it on one slide. So what you want to do is I give you a matrix A with non-negative entries. That's an n by n matrix. And what I want you to do is I want you to rescale the rows and the columns of this matrix with positive numbers such that the new matrix B, which you get out here, has row and column sums approximately 1. So it's almost doubly stochastic. I mean, ideally, you would like it to be exactly doubly stochastic, but this is not always possible. So approximately is pretty good enough. And you might wonder, what does this have to do with convex optimization? Right, it's some funny looking linear algebra problem. But it turns out that a good way you can analyze this is by looking at some funny function, which I'll call f. And basically, I think of this like these x and y that I use to rescale. I think of them as my variables. And then the function you can write down. It's
Darius testing all of us. I don't know why.
all right. So you can write down some funny function. Okay, it doesn't matter so much whatever this expression is. What matters is that, okay, like it's not. It turns out that this term. Oh, oops, too far. It turns out that this first term it's not convex. If you think of it as a function of this x and y. It takes a little bit of computation to see that this is not true, but it's true that it's not convex. But you can do a reparameterization of this domain. Right, you can think of these capital X's as like e to the little x, and these capital Y's as e to the little y. And then it turns out that if you think of f as a function of these coordinates, it is convex. Right, and why is this related to this talk? Well, it turns out that if you look at the like the positive orphan, you can put a metric on it, which is exactly the restriction of this affine invariant metric on this PDN space. Such that the geodesics are exactly these e to the x's. Right, so it becomes like geodesically convex on this space of x points. Right, so it's convex after this reparameterization. And now, why do we care about doing this stuff on manifolds, right? This is now like ordinarily like Euclidean convex after this reparameterization. And you can also solve it very efficiently using recent stuff, but what's important for us is that there is some generalization of this matrix scaling problem, where now you're not using that, like you're not using diagonal matrices anymore, but you're using this sort of arbitrary matrices, which we know to be equivalent to also solving some optimization problem. Like you can write down a potential function, you can reparameterize this to be like some optimization over a bunch of matrices. And we know that this reparameterization is now geodesically convex. If you think of this like space of determined one matrices as using this affine invariant metric. And like the important result here is that whatever methods we had previously for scaling problems, even though they're not efficient, we can recover the previous state of the art, essentially. So people have thought about these problems for a long time, and I think we're still pretty far away from like polynomial time algorithms, even though we believe that they should exist. But sort of our main motivation essentially for this work was, all these previous methods that we had for solving these types of optimization problems, we know that they're like good obstructions to polynomial time algorithms. But interior point methods could become faster. Okay, we don't know how to make them faster than whatever was there previously yet, but we have hope. There are also some other geometric applications which I will just skip in the interest of time. All right, so let me end with some open questions. Right, so these barriers that we constructed, for instance, for this ball, its radius, it scales with the diameter of this ball. Right, this is pretty bad for applications because if the domain you need to look over has like large radius, then you can't get something efficient using just that. So it would be amazing if you could find better barriers or prove lower bounds. And I'm pretty sure that actually like these R-squared things are optimal, at least for balls. So maybe balls are not the right domain to optimize over. It would also be really cool to be able to write down for any complex domain the self-concordant barrier. So it turns out in the Euclidean case, people have worked hard. Like there are various constructions known, which are also like pretty efficient. But in the in this manifold case, we don't know how to construct like a barrier for complex domain, or for every complex domain, I should say. And I also talked about like only the the case where you have like this where you want to implement this path following method, starting from a good like starting point, which is close to this central path. But maybe you don't know exactly where such a good starting point is, so you would have to find it first. In the Euclidean case, you can actually find a good starting point from any feasible point using like a reverse path following method. But it's not clear how to carry out like a similar trick in the manifold setting, mostly because there are very few linear functions. And lastly, I think it would be amazing to also give like a generalization of primal dual algorithms to this setting. The big complication here is that like there are some good notions of dual, but sort of the dual is not necessarily a manifold, and like its geometry is much harder to understand. You know, lots of open questions here. And with that, I would like to thank you very much for your attention.